realize that maybe too many students rely on that. I have 75 students, I only have 46 of you around, okay? So tell your classmates to come. Another way is that I will delay posting the record classes. Okay, let's continue. Summarizing those Stern-Gerlach results. There is a new magnetic dipole moment attached to the electron. It is related to a proposed new angular momentum called spin angular momentum. And the relationship is in opposite direction for the reason that electron conventionally is given negative E charge. And there will be a ratio. This ratio goes like E over M without the 2 in the denominator. It is an experimental fact to start with. Okay, so this box summarizes the Stern-Gerlach experimental facts, whereby we also introduce a new thing, a new property to the electron. It is called the spin's electron, electron's spin. Generally, later on, we found that every particle can carry a property called spin. So generally, when a particle with charge Q and mass M, we say that it has a spin S, then the accompanying spin magnetic dipole moment is given by this expression. At this point, you see one new thing. There is a G factor called G factor of spin, G subscript S. This is in complete analogy with the orbital expression that we discussed a while ago. The new thing is that this G factor is experimentally found to be 2, so that it's 2 canceling this 2, and electron has charge minus E, thereby it agrees with this experimental fact. From experiment, we only saw 2 beams coming out, thereby this S in any direction called Z can have only 2 components, okay? And this G factor worth another story. The reason most accurate number is this. Again, I go into this National Institute of Standards and Technology, 標準局, and then you can look up what is the latest, most accurate value for this G. Okay, it is this number. In our course, we will take this G equals 2 to be a good approximation. We will stick to this GS equals 2. But let me tell you that this G is a very important number in the development of physics, because the discoverer's spin start something related to relativistic quantum mechanics. Spin comes out most naturally from the relativistic theory of an electron. That is Dirac's theory. That won Dirac half of a Nobel Prize, and in his equation that is analogous to Schrödinger equation, but with Einstein's special relativity embedded in it. What I meant is that Schrödinger equation start with the kinetic energy being half mv square, or p square over 2m. Okay, so this is Newtonian. And Dirac immediately after 1926, when Schrödinger published his papers, Dirac thought there must be a way that he can make quantum mechanics in line with special relativity. So he tried and tried, and then he found an equation called Dirac equation that works for the electron. His equation turns out to be a matrix equation of size 4 by 4. The mathematical structure cannot be smaller than that. That's what he found. If he wants a wave equation like Schrödinger's for the electron's wave function, the smaller size mathematics involved is 4 by 4 matrices. And then the solution, the wave function, that is to say the solution is 4 by 1. 1 by 4 or 4 by 1, I'm confused. It's a column. 1, 2, 3, 4. Okay, 4 things in a column. And that 4 things in a column turns out to be something very important. It has spin embedded into it. Okay, so roughly, the answer is like there are 4 entries. Okay, if you take only 2 entries, 2 and 2, okay, the 2 by 1 thing is exactly what you learned last term in the spin matrices. You have seen the Pauli matrices, right? Right, you have seen that, right? I saw in your notes, okay? So you have this Pauli matrix sigmas, you have seen that. So this 2 by 1 part is exactly a form to represent both the Schrödinger thing, the electron's wave function in space, as well as the spin situation. Is it up 1, 0 or down 0, 1? Okay? But then why 4 by 1? What comes up from Dirac's solution is that he did not only get some solutions for positive energy of positive energies for the electron, he also get negative energy solution for the electron. He didn't give up. He said these solutions are there, really there, okay? Later on, that becomes antiparticles, and positron belongs to that part of the solution, okay? So that is the story. And that story goes on for at least half a decade, half a century, because starting from there, that is only an equation for electron. And then from there on, we have the idea of electrons interacting through the EM field, the photons. Thereby, afterwards, with the further development is that the Dirac equation becomes the basis, the starting point of developing a field theory called quantum electrodynamics, in which the electron part and the EM wave part, they are both forming part of a full Hamiltonian. We have electron, we have EM field, we have how they interact. That becomes quantum electrodynamics. in which we can actually calculate from this theory what is G. And the answer is as accurate as this. You can look it up. You can Google G, QED, most accurate result up to now. I think it is good up to something like the 12th digit or the 13th digit from calculation comparing with experiment. And this is always claimed as the most accurate physical theory ever, the QED, I mean, okay? So this G has a very interesting and important part to play in the development of physics. But for us, let's go back to a humble task. G is 2, okay? Don't worry about fancy thing. And then that is how spin give us the spin magnetic dipole moment, okay? Then the Stern-Gerlach experiments need us to think about spin half being the spin angular momentum of an electron. The half comes from the fact that you fly in the hydrogen atom, only 2 beam comes up and the diffraction is of equal amount, higher, lower, okay? That is interpreted into 2 values for the Z component of the magnetic dipole moment of spin. Therefore, also only 2 possible values for the Z component of the spin that goes with the electron. Okay, that is how it comes from experimental science. Therefore, nowadays, we claim the electron is a spin half particle. The most important concept is that this property is an intrinsic property of an electron. Okay. In Cantonese, I think the term is something like 固有的啊，是电子固有的一个特性啊，係電子固有嘅一個特性。Intrinsic, the opposite of which is extrinsic. Orbital angular momentum and orbital magnetic dipole moment of an electron is an extrinsic property. By that I mean the strength of it depends on which particular state the electron is in. L equals 0, S state, none, 0. L equals 1, you have stronger orbital angular momentum. L equals 2, you have even longer vector for the angular momentum. Okay, that is extrinsic. But intrinsic, it means no matter what the electron is doing, it always carries that property with it, just like the charge, right? Charge minus E, an electron here, an electron attached in an atom, a free electron, an electron on the moon, minus E. Okay, that is an important concept. So let's work out. Let's remind you of more about spin. The S square, the magnitude square, is S times S plus 1 h bar square. S is half, thereby it is a constant. Okay, so take this with you. Electron has a constant strength for its spin angular momentum. Okay, the strength is square root. This is the magnitude of the spin of an electron. Square root 3/4. Okay, and unfortunately, not many people care about this, but this is a fact. It's not varying, and that emphasizes the point that it is an intrinsic property. And therefore, from experiment, we see that this spin can only take on one boring value. The quantum number is always half. Okay, I must emphasize that it is always intrinsic. Okay. And that comes with the Z component, or any component in that matter, can only take on two values because ms can only be plus minus half, given s is half. And that goes in agreement with experimental observations. Therefore, you will always see this kind of notations, and you use that in your previous term for the spin description. We can use the S and ms formally to describe this state. For example, electron always have S equals half, and then ms could be plus minus half, or in short notation, it can be something like that, okay? And usually ms is plus half. Some jargon said it is a spin up, it is spin down, okay? And some use a column vector. I will use alpha to be 1, 0, and beta to be 0, 1 for the Z direction Pauli matrices, okay? So this all means the same thing, okay? Now, given that electron always has S equals half, very often we are so lazy that we don't even mention this first half in the notation because it's always half, the boring half. Sometimes we only mention whether ms is plus half or minus half, that is up or down. Even mention it is square root 3 over 4 h bar in length. Okay, not mentioning that. That is half in front. And this is the vector model that is worth carrying with you, especially for those who want to have some idea about what spin is and then go into doing experiments. You know, spintronics is a very hot field, playing with the spin part of an electron rather than the charge part of the electron. Electronics, that is the most important thing that you are using day in and day out with your mobile phone, your computer, your tablet. That is electronics, making use of the charge of the electron. But after discovering spin for 100 years, 1922, we are approaching 2022, still very few technologies relied entirely or only on the spin property of the electron. But in recent years, there are rapid development, and in fact, many of the storage, the hard disk thing, they are more related to spin of electron than charge of electron. Writing, reading, things, that is a field called spintronics. Okay, for your generation, there may be something that you should be aware of, okay? Because you are the next generation of physicists, or you may be the next generation of some company's CEO. Therefore, where you need to make investment decision, you know what is going on, what is the future, okay? So this is a part. So this vector model helps us think. It is like we have a vector that longer, right? This one. Okay, this one. So the length is a constant, and then nonetheless, any component, say Z direction, any direction, it has only two projections, okay, possible projections, plus minus h bar over 2. And therefore, one constructs such a classical model just to help us remember the feature. Okay, don't take it very seriously, but it's a very useful picture. And I also know that you have seen all these Pauli matrices last term. I just write them out here for completion, for completeness. You should review spin part if you need that knowledge. So summarizing spin, okay? So we have this constant magnitude. S is always half for electron, okay? And then ms can only take on two values, up, down, so-called, okay? And now that also comes with a spin magnetic dipole moment, and the G factor is 2, okay? That is to say, the ratio is minus E over M. Now, let's go back to the discussion of the spin magnetic dipole moment. We have this relationship. Let's work out some property of this spin magnetic dipole moment. We just learned how long, the magnitude of this vector spin of an electron. It is boring this. Therefore, every electron also has a constant length for the magnetic dipole moment from spin. It is 1.7 Bohr magneton, okay? Square root 3, about 1.7, okay? So it's a constant. It's always intrinsic property of an electron. And that is very important, okay? I will elaborate it a little bit further. And now let's look at the Z component. It is proportional to S, therefore SZ will give the S component of the spin magnetic dipole moment. Recall that this can only take on plus half minus half H bar. We plug this value in. Here is another reason why I said you should remember Bohr magneton by heart. An electron has in any direction only two projections, two possible values of the spin magnetic dipole moment. And they are plus minus Bohr magneton. Isn't that simple? Okay. Now, if there's a B field, thereby mu B times B will set the scale of how spin interact with external field. Get me? So I think this is the most important reason why we better remember mu B, the Bohr magneton. It is the elementary unit of electrons' spin magnetic dipole moment. Not even with a square root 2 in front, not even with a square root 3 in front. It's just plus minus mu B. That's the projection in any direction. Okay? So this is the take-home message. Okay? Now, the important point about this spin magnetic dipole moment is that is the origin of magnetism. We have magnetic materials, iron, cobalt, nickel, something like that. Only, or not many, only a few in the periodic table, okay? But why they are magnetic? In high school, or even primary students have told me this, atoms behave like tiny magnets. Well, again, it is a statement so broad and so vague that you cannot rank it as right or wrong, okay? But at university level, a better understanding is that, yes, some atoms, the periodic table, only a few of them are magnetic. Some atoms behave as tiny magnets. That's baby level. Add to it, it is due to the effect of spin magnetic dipole moment of the electrons in the atom. That is quantum mechanical in nature. We will see more about this later on. When we go into molecules, we have a better understanding of why. It is the electrons' alignment that give rise to the atom's magnetic dipole moment. And when atoms form a solid, maybe there are some effect that this atom's magnetic moment wants the neighboring magnetic moment to be aligned with him. By propagating this intention of alignment through the solid, all will align together in the same direction, and you have magnetic property. And that is the reason, okay? Very quantum mechanical in nature. Although magnetism is often regarded as the oldest science subject in human. In China, we have this 皇帝有嘅指南車，皇帝有嘅指南車, right? So it's using something related to magnetism, things like that. It is an old subject, nonetheless. The real understanding started in 1926 when quantum mechanics came up, and Heisenberg played a leading role in the understanding of magnetism. We will have more to say about it, but it's all spin, okay? That's the point. Now, with this reminder of spin in a more physical sense, instead of formulas, we can now include spin into the atomic wave function. I must say that if we use Schrödinger's quantum mechanics wave equation, Schrödinger equation, this spin part has to add into the Schrödinger equation as an extra part. The spin does not come out naturally from Schrödinger equation. There's no way, because as I said, Schrödinger started out from Newtonian mechanics, okay? But we know after 1922, there are spin. So this spin part is a product multiplying into the wave function you solved from the Schrödinger equation. And that is what Pauli did in 1924, again, before Schrödinger, Heisenberg did the quantum mechanics. He was trying to make sense out of the periodic table, the periodic table known at that time. He needed a fourth quantum number in his language. And now we understand this fourth quantum number is referring to MS. Remember, without spin, you solve it, and then we have this, say, for example, ground state is 1, 0, 0, N, L, ML. But now with spin in our mind, we could further label this state with a description on the spin of the state. For example, 1s spin up. Then you have the 1s, and then you have this 1, 0 spin up, okay? Or, as Pauli required, invoke a fourth quantum number that has to do with MS. Okay? Now, actually, we may need 5 quantum number. Remember, this MS is under S equals half, spin half of electron. Okay? But because electron is always spin half, this half is saved, not shown. Therefore, a fourth quantum number referring to MS. 1s down, so it is this. Okay. Now we are at the time to motivate what comes next, what comes further. All right. Now, with this idea, it started to motivate us to think about two questions. Let's think about it this way. How about 2PZ? That is 210, okay? And now, how about spin up, for example? Then we have this 10, that is 2PZ up, okay? In explicit form, we have this multiply into a spin part. In the physical sense, since L is 1, the orbital angular momentum is not 0, it's finite, square root 2 h bar. We can think about it as follows. This electron is orbiting around the nucleus. Okay, L is 1, not 0 at least. Right? At the same time, we just discussed that every electron has an intrinsic spin, and thereby it has an intrinsic spin magnetic dipole moment. The spin is non-zero, it's a constant. Okay, and I represent it by an arrow up here for the electron in this state, okay, just to make it more pictorially. Now think about the situation, the orbital part. The electron is orbiting around the nucleus, and itself also has a spin, angular momentum. It is carrying two angular momenta, an L and an S. Question number 1. Does it make sense to think about a total angular momentum S plus L? Well, at least that is a good question, I would say. When you have two things, you may wonder, oh, they are of the same nature, angular momentum, something of unit h bar. Does it help? Does it do any good to define a total angular momentum? Okay, we have a long way to go to answer this question. Second point, how about this? If I'm sitting on the electron, what I will see is this nucleus circulating around me. See my cross? So I depict it here, I sit here, then I'm seeing the nucleus orbiting about me. But this is a proton, for example, in hydrogen atom, therefore it's a current loop. And thereby, the place that I sit here experience a magnetic field due to this apparently motion of the nucleus. However, the root of this thing is the electron's own motion. It is easy to imagine because this relative motion actually comes from the orbital motion of the electron. The field generated should be proportional to the orbital motion of the electron. Thereby, there may be a coupling between the magnetic dipole moment due to spin, the arrow here in opposite sign, okay, with its own orbital motion, because that will generate a field at its own position. Okay? Follow me? So once we have S comes in addition to L, there are new games, new questions. For question number 1, does it make sense or do any good to define the total? A better way to appreciate and to answer this question is to learn something about the general properties of angular momentum in quantum mechanics. That will be the next section. For the answer to the second question, will the electron's motion generate a field to couple with its own spin magnetic dipole moment? The answer is yes. This effect is called spin-orbit coupling or spin-orbit interaction. These are the two topics that we would like to explore in the next few sections. I would like to motivate a bit what we will do next Tuesday. It will be a very long section, rather mathematically, but I think it worth the effort, okay? But let me state the question at the outset. We have seen orbital angular momentum obeying 6 commutation relations. Lx, Ly, y, z, zx. So I only write down one, and I let you write down the other. And another 3 has to do with L squared with Lx, Ly, Lz respectively, and I only write down one. You write down the other, okay? And we have seen the same structure. You have seen the same structure last term about the spin x, y, z operators and the s square operators. So they have the same mathematical commutation relations. More, when you solve the atomic problem, explicitly you have seen these are the eigenstates. And when you have a given L, ML must go through 2L plus 1 values. We just remind you that for spin of electron, S is half, and the MS again go from S to minus S. So L to minus L, S to minus S. There seems to be some kind of universal feature of this behavior. So we would like to explore the following question next time. If we only focus on the commutation relations, that is to say, we use this and no more than that, only these 6 relations as definition of an angular momentum in quantum mechanics. Okay? What will be the allowed form of the eigenvalues and eigenstates? Now, that is a very general question. Okay? We will not represent it as theta phi derivatives. We don't want to. We do want to do everything based on commutators. Why? We want our results to be applicable to orbital, to spin, to the total, to something later will appear, nuclear spin, or something even not existing. The theorists call it isospin, something that looks like spin. So broadly speaking, we will take this 6th thing as the definition of an angular momentum in quantum mechanics. Meaning, if you find a vector, it has 3 components, it has a magnitude, these 4 things obey this set of commutation relations, we will broadly define that as an angular momentum. Then we ask, based on these 6 relations alone, what will be the allowed, the possible eigenvalues of Lz and L squared? Okay, so this is the question we will discuss next Tuesday. There are 10 pages of mathematics in the derivation, but I will first give you the major result. If you don't care about the derivation, fine. You know the result, that is the most important, and then move on. Okay, so that is the plan next Tuesday. So I will stop here today. I will stay for a while if you have questions. Okay, so long for now. See you next Tuesday.